Hello everyone, welcome to my channel. Myself Vignesh Anand. In last two parts, we have completed up to the emitted turn of thyristors. So if you want to refer the before videos, we can refer my before videos also. So in this video, we are going to see about the bidirectional current, bidirectional controlled thyristors, then integrated gate commutator thyristor, then static induction thyristor, then TRIAC and DIACs. So these are all the types we are going to see in the third part, and this is your final part. Then bidirectional controlled thyristor. So the BCT uses two thyristors in an anti-parallel configuration in a single device. So bidirectional thyristors that are able to conduct a current in both the directions when it is triggered. So in the name itself you can came to know that it will conduct when forward direction also, and also for your reverse direction of current flow also. So it has a two separate gate terminals, one for each thyristors. So one will be used as your gate as a turning on, and then another one be used for your turning off. Bidirectional phase controlled thyristor came to replace the BCT by bringing the advantage of increased surge current, then reduced cost. So BCT, this is your BCT simple diagram. In here we have two thyristors, and one will be as like a one will be for your forward current conduction, then another will be for your reverse conduction. Next is your integrated gate commutated thyristor, IGCT. So the IGCT integrates a gate commutated thyristor with a multi-layer PCB board for gate drives circuits. So the IGCT is turned on by providing a gate current. It is turned off by a multi-layer PCB, which means your printed circuit boards that are provides a fast rising then large current of approximately 4 kilowatt per microsecond. Then it drains out all the current from its cathode and it turns off immediately. So this IGCT is your advanced thyristor triggering modules which is used in your uh, field. Then it combines the performance of thyristor and turn off character of your transistors. It has a main featured as a high current capability, then and also a low on state voltage. Then the conducting state of your IGCT is a regenerative thyristor. Then the blocking state is a gate cathode junction is reverse biased and out of operation. So it is like a normal thyristor only for conducting and reverse blocking states. Then no external dV by dt protection is needed for the IGCT because it becomes a transistor for withstanding blocking voltage. So turn off occur after becoming a transistor only. So we don't need a snubber circuit. Normally the snubber circuit is used for your dV by dt protections also. So in this case we will overcome these unwanted costling also. Then application, it is normally used in your digital circuits, then for AC and DC motor speed control, then for your light dimmer circuits. So it is advanced turning on and turning off of your thyristor. This is your symbol of your IGCT, anode and cathode, and then the gate terminal is given. Then coming up to the static induction thyristor, SITH. So the SITH is a self-controlled similar to a gate turn off thyristor. A SITH has a three terminals, namely as a cathode, anode and gate. It offers the capability of conducting a large current at a low value of a forward voltage and also gets turned off quickly. The SITH exhibits a higher value of conduction drop. then it exhibits a high switching frequency. Then the rate of change of voltage and current is respective to time, and also it offers a safe operating areas for operations. Then coming up to the working of SITH. So the presence of zero voltage between the gate and cathode, the device is in on state. However, the on state performance gets improved with a small positive gate voltage. So while to turn on this device off, a necessary gate reverse voltage is required. So the turn on conditions, forward biased condition of your anode irrespective of zero voltage at the cathode terminal, the device act as a diode. Basically, when a voltage is applied with respect to the cathode, then it makes positive junction forward biased condition for the load of your which means for carrying out the load current from anode to your cathode. Then coming up to the turn off conditions, under a forward biased condition of your anode, when a gate terminal is reverse biased relative to the cathode, then it will cause a formation of depletion layer on your p-n junctions. Then due to this depletion layer, the anode current now stops flowing from a anode to cathode. So in this way the turn off will occurs. Then its main application, it is used in your HVDC converters along with the induction heating. Then it is used in high frequency power conversions. Then used in your energy accelerators, and also used in your current source inverters. This is your symbol of your SITH. So it is also a normal thyristor kind of thing with some changes in the operation. Then DIAC, diode for a alternating current. It is a bidirectional semiconductor switch that can be turned on in a both forward and reverse direction. So DIAC, in the name itself, you can easily know that it is a diode type of a thing. So only the turning on of your diode is possible. The diode, which means the DIAC, starts conducting electric current if the applied voltage goes beyond its breaking over voltage. So a DIAC is simply a two diode connecting in a parallel and opposite to each other. It since the diode is a bidirectional, the terminal of your diodes are simply known as MT1 and MT2, which is your main terminal 1 and the main terminal 2. Diode does not have a controlling gate terminal because they do not turn on or off by simply reducing the voltage below the avalanche level breakdown, and it can be done in both the polarities. So it delivers a symmetrical switching property in both the polarities of your applied voltage. Applications, it in combination with the TRIAC, it is used in your symmetrical operation of your circuits. Then this is your symbol diagram of your DIAC. So as I said, it consists of two terminals. One is your MT1 terminal and another one is your MT2 terminal. And in here the MT1 and MT2 is given by their polarities interchanging. Then coming up to the working of your terminal, consider the MT1 terminal to be positive, then the P layer near the MT1 will be activated. So the conduction will take place in a order of P1, N2, P2, N3. When the current is flows from a MT1 to MT2, the junction between the P1N2 and P2N3 will be a forward bias, and the junction N2P2 is reverse biased. Then if consider the MT2 terminal be positive, then the P2 layer near M2 will be activated and the conduction will take place in order of P2 N2 P1 N1. The current will be flows from a MT2 to MT1 on the junction P2N2 and P1N1 are in a forward biased and N2 P1 will be in a reverse biased condition. Please refer my before diagram for just understanding. So this is your conduction cycle or a graph of your DIAC. So as you know, the blocking state will be for a minimum amount of voltage whenever the breakdown takes place, which means the point A to B, the conduction positive of will be takes place whenever the normal breakdown voltage reaches over the avalanche breakdown, which means the avalanche breakdown takes place when a normal breaking voltage will be over the limit means it will takes place automatically. So the same will be for your negative half of the cycle. Next, coming up to triac, triode for a alternating current. It is same like a diode. Additionally, we have a gate terminal. So in this way, a controlled triggering can be takes place in both the direction, which means for forward and reverse conditions also this controlled triggering can be made. The triac can be a conduction state if the applied voltage is equal to the breaking voltage, but most preferred way of turning on a triac is providing a gate pulse, either a positive or negative pulse. If the gate pulse is high, a very small amount of voltage a very small amount of voltage is enough to turn on the triac. So it is characterized by a different modes of operations. First thing is that M2 is positive with respect to M1 with a great polarity positive with respect to M1, which means MT1. If P2 is positive, if MT2 is positive with respect to MT1 with a gate polarity negative with respect to MT1, then MT2 is negative with respect to MT1 and gate polarity negative with respect to MT1. Then MT2 is negative with respect to MT1 with a gate polarity positive with MT1. So these and all the various modes of operations takes place in your triac. Next is this is your triac diagram. Here we have a MT1 and MT2 terminal and also a gate for a triggering or a controlled turning on and off of your triac. So this is your P and PN junctions given in here, which means the two thyristors which is parallelly connected. Then this is your conduction state and blocking state of your triac. In here the modes of operation, as I said, that is given in your quadrilateral 1 and 3. So the applied voltage which overcomes the breaking voltage, the conduction takes place. Further the turning on of your thyristor is done. So these and all the things which is in your types of your thyristor. Hope you understand. I think so. For this, for each and every thyristors, we can make a brief videos individually. Hope you understand. I think so. See you in next video. Have a nice day. நன்றி, வணக்கம்.